Good morning, dear participants. Welcome to the last day of Blockchain and IoT Refresher Program. Let me take this opportunity to introduce our first session guest, Dr. Vinayaka Pandit. Dr. Vinayaka Pandit is a senior member of technical staff at IBM Research. He leads the blockchain and supply chain research strategies for IBM Research. His current work in blockchain and supply chain research brings advanced techniques from operations research, cryptography, security, machine learning, and blockchain together to enable a privacy preserving collaboration on multi-enterprise business networks. Dr. Vinayaka started his career in IBM Research in 1999 as a research staff member with a focus on approximation algorithm and combinatorial optimization. His work during this time resulted in some of the classic results in facility location, local research heuristics, scheduling, and network designs. Dr. Vinayaka obtained his PhD in computer science from Indian Institute of Technology, Delhi. Sir, it's a great honor to have you in our session, sir. And yes, sir, you can start the session now.
Um, just give me 1 second. I'm not able to share my screen. I'm using an Apple laptop. I don't know. I generally with Zoom, WebEx, and all screen sharing is not a problem, but it is giving me some trouble. Just give me 1 second. Let me just figure out what I need to do.
Sir, few minutes back we have seen that you are presenting messages come, sir, on the screen, but later it is disappeared.
See, I'm trying to present. I'm trying to say okay. Yeah, I'm still getting this same issue. Uh,
Sir, can we do one thing, sir? If you share your PPT, I'll present from my screen.
okay. Shall I email it to you?
Email, WhatsApp, anything will work, sir.
Okay. I'm emailing it to you. Just give me a second. Okay, I have sent it to you on your email. Can you please check it? Did you get my email? Can you please go to the full screen mode? Full screen, the full screen mode, Control L. Okay, go to the next chart, please. Hello, everyone. Shall we get started? Okay, I'm assuming. Okay, fine. Okay, thank you for joining this session. My name is Vinayak. I'm from IBM Research. So here is the outline of the talk, right? So I don't know how many of you are familiar with blockchain, etc. So what I'm going to do is I'm going to give a very simple introduction to the problems that blockchain aims to solve, right? I think it's important to appreciate the problems that it is trying to solve, okay, and what kind of a solution it gives. After that, I'll give you an overview, again, not the full nuts and bolts details, but an overview of the key components of the blockchain technology. Could one of you just indicate to me that you are able to hear me clearly and see the charts clearly?
Yes, sir, we can hear
Yes,
you.
we can hear
Okay,
you
okay,
and we
thank
can
you.
see the presentation. No problem.
Okay, thank you. And then what we will do is we will look at one key element, which is called the consensus. Okay, and I'll explain to you what all this means. Right, that we will try to understand in some more detail. Right, and then what I will do is I'll give you a view of how does a blockchain project really get implemented in the real world, right? I mean, what does it take, how does it look like, etc. And it my experience, of course, comes from a special type of blockchains that we use for enterprise solutions, right? I mean, it is not based on some of the public blockchains, but it's not very different. Yeah. Okay, go to the next chart. Okay, so we'll begin with a very simple example of a supply chain coordinate problem that occurs in supply chain coordination, right? And any of you who has worked in any manufacturing setting or supply chain settings will be familiar with something like this. Okay, we have a simple picture here. We have 4 players. Okay, we have a manufacturer that I have named as M, and we have 2 suppliers of parts or components called S1 and S2. Okay, and we have a 4th player called assembler, okay, denoted by T. Yeah, and what we are going to do is look at a specific problem that occurs in this setting, which is called build to ship to pattern in manufacturing. Okay, so what it really means is that the manufacturer wants to get some components from S1, wants to get some components from S2, but those components need to be assembled to build a larger unit, and that's the larger unit is what the manufacturer is interested in. Okay, so what the manufacturer does is he gives 3 orders, purchase orders, okay, PO1, PO2, and PO3 to these 3 players. Okay, the purchase order 1 to supplier 1 says that please ship 10 units of your component. Let's call that component as A, right? Ship 10 units of A to assembler. Okay, and purchase order 2 says ship 10 units of B to assembler, and then the purchase order 3 tells the assembler to assemble 10 units of a larger component called C by utilizing 10 units of A and 10 units of B. Okay, so this is a very typical setting. Okay, especially in the way the automotives are manufactured, right? I mean, this is a very typical setting. Okay, like big auto manufacturers, whether it is Bajaj or TVS or Maruti and so on, they have this kind of setting very commonly. Okay, so they will be buying parts from somebody, but the part will not come to their premises, but it will go to an assembler who has to do the assembly and then send it back. Okay, we will assume that the price, the unit price of the component A is 1, the unit price of component B is 1, and the unit price of assembling, right? By taking 1 unit of A and 1 unit of B and producing an assembly called C, costs, let's say, 5 rupees. Yeah, I hope the setting is clear. Go to the next chart, please. Now, what would you expect in a setting like this, right? You would expect that these activities like shipment 1 which goes from supplier 2 to assembler, shipment 2 which goes from supplier 1 to assembler, and then assembler receives those events, right, ships the units back, right? And if everything goes well, right, the S1 should expect 10 rupees from manufacturer, S2 should expect 10 rupees from manufacturer, and the assembler should expect 50 rupees from the manufacturer, right? I mean, this is if everything goes as expected. Okay, but suppose, right, after all these things, let's say these transactions take place, and then the manufacturer sends a message to everybody, right, as follows. The manufacturer says that I am supposed to pay 9 rupees to S1, 9 rupees to S2, and 45 rupees to the assembler T, because I received 9 assembled units and not 10 as I expected. Okay, now everybody is in for a surprise, right? I mean, the other 3 players. So can you go to the next chart, please? So, let's basically say what could have actually happened in the process, right? Let's say that one scenario is that one of the component of A was faulty, right? And therefore T could only assemble 9 units of C, right? And in that situation, what should really happen is that M should pay 9 rupees to S1, 10 rupees to S2, right? 45 rupees to T, right? And and also say, make a note that T is left with 1 unit of B for future assembly, right? But what happens today is that this is not the way it happens, right? Because each of these companies are maintaining this information in their own systems. They don't have a common visibility. Okay, and the entire confusion occurs when the time for the big manufacturer comes, right? The time to pay, right? That's when everybody recognizes, and then everybody is making frantic phone calls or sending emails saying that, oh no, this is what happened, that is what happened, etc. So this is one scenario. Go to the next chart. In scenario 2 is exactly the reverse of that, in which case, let's say the component B was faulty, and again, M is supposed to pay 10 rupees to S1, 9 rupees to S2, and 45 rupees to T, right? Go to the next chart. Then it is also possible, the third scenario is that there was no faulty component in S1 or S2, but there was really an assembly error, right, at C, in which case M should pay 10 rupees to S1, 10 rupees to S2, and M should pay 43 rupees to T, because 45 rupees for assembling, but 2 rupees for spoiling the two components, and 43. Right? This could be the third scenario. Go to the next chart, please. The fourth scenario is that everything went fine. All the 10 assemblies were good. All the 10 assemblies were received at M, right? But somehow, either because of pilferage or whatever it is, one unit gets lost from the inventory at manufacturer. So manufacturer only registers 9 and hence sends this particular message, right? So any one of these scenarios could have happened, right? And this message from M comes like this, right? Essentially, when M recognizes that M has got 9 units of assembled unit, right? This is the message that manufacturer sends. So any questions, confusions so far? I have basically, what I have said is that I have painted a picture of the problem that occurs in supply chain coordination, and I have given you a situation where at least 3 of the players are surprised by the message that comes from M regarding the settlement, and then I have kind of drawn out 3 or 4 possible scenarios that could have led to this surprising scenario. Okay, any questions, doubts at this point in time? Okay, so basically why this happens? This happens because everybody is maintaining their own systems and they are not able to reconcile the truth at every point in time, and suddenly, all of a sudden, after a lot of water has flown down the bridge, they have to they reach a stage of confusion and they need to kind of clarify amongst each other. Go to the next chart, please. Next chart, please. Okay, so I will not repeat this. This is what I told, right? I mean, this is how it happens today, right? People resort to ad hoc reconciliations, portals, email, faxes, phone calls, and so on, right? And it's very time consuming, error prone, and it's more importantly, the last point is very important. It's subject to asymmetric relationships between the entities, right? I mean, as you can imagine, in a manufacturing setting, like if it is a big auto manufacturer M who is doing coordinating all these things, they have a disproportionately higher strength, and people will have to kind of accept whatever they say as the ultimate truth, right? I mean, this is the problem that blockchain is trying to solve. How exactly? Let's go to the next chart. Next chart, please. Okay, so what would be an ideal solution, right? An ideal solution is that, and this is what blockchain tries to provide, right? Let's say that all of them are together, okay, not individually, but together they are maintaining a common ledger, okay, that is replicated in each one of these places. Okay, and whenever any activity takes place, whenever there is a need to update the content of any of the ledger, the updation happens at each one of these ledger locations. That's why it is called a distributed ledger. Okay, meaning it's the same ledger which is replicated amongst all the interested parties. Okay, and an important thing about the way this ledger is maintained is that no one can unilaterally change their copy of ledger. Okay, we'll show how this happens, but that's the property that the technology will give us. Okay, one is that it will give us this property that everybody is able to maintain a local copy, and all the local copies evolve in sync. 1, 2, nobody can unilaterally change just their copy of the ledger. And then more importantly, you can register contracts. Okay, we call them as smart contracts, which automatically get executed based on the state of the ledger. For example, it could say that the moment a shipment happens from supplier to assembler and assembler acknowledges that I received so many components correctly, the smart contract will say that the manufacturer has to immediately pay the supplier, irrespective of the assembly, right? And that's what a smart contract is. Okay, so suppose these were the suppose somebody gave us a magical solution which satisfied these properties, then how would the world look like? Let's go to the next chart. Okay, so see, for each of the entities I am maintaining a ledger here, and manufacturer releases a purchase order to everybody, and everybody's thing basically makes a copy of this, saying that okay, at the beginning manufacturer M released 3 purchase orders, PO1, PO2, PO3. Go to the next chart, please. Then let's say the shipment happens from both the people. Then it says that shipment happened from S1 to T and S2 to T. Go to the next one. Then let's now say that all the 10 units from A and B pass the quality test, right? Then that also gets recorded. Okay, at this point in time, T has not yet started assembling. Okay, T cannot say that I only received 9 units of A and 9 units of B, because if he tries to say that, S1 and S2 will disagree, saying that I sent 10, you show me a proof that one of them is faulty, right? Either assembler will have to show a proof that one of them is faulty, or correctly register that all the 10 pass the quality test. In this scenario, let's assume that all the 10 pass the quality test. Go to the next one. Okay, that's exactly what I said. Go to the next one. Yeah. At this point, okay, let's say when this assembler is actually doing the assembly and fails to do one of the assemblies correctly, right? Then the assembler has to acknowledge that they are sending only 9 units, and hence there was one assembly that went faulty, right? Because of which the assembler will be penalized. Okay, so this is the power of the blockchain technology, okay, wherein everybody is saying the same version of the truth at every point in time, and at every point in time, whatever gets into the ledger is based on the consensus amongst all the people that are involved. Okay, and 3, nobody can unilaterally change just their local copy of the ledger. Okay, so this is the property, these are the properties that blockchain gives us. Okay, go to the next chart. Yeah, exactly this is what I'm saying, that in this scenario, there is no confusion. M has to pay 43 rupees to the assembler, and everybody is satisfied with this. So if you don't take anything else from this talk, it's perfectly fine. But this is the message that you need to go, right? I mean, go to the previous chart. Yeah, this is the picture that you should carry, right? Everybody is maintaining, there is a network, and in the network, whoever is participating is maintaining a ledger. It's a distributed ledger in the sense that distributed replicated ledger in the sense that everybody is maintaining the same version of this ledger, and each entry is made with the consensus from everybody in such a way that nobody can cheat and nobody can unilaterally deviate from others. Okay, so these are the desired properties of a ledger system that blockchain gives. Okay, so this is what you should like at least this picture you should have in your mind, that this is the problem that blockchain as a technology is solving. Okay, go to the next chart. Next one. Okay, so this is one motivation, and this motivation comes from the area in which I work, which is, you told in the beginning that I work in operations research, which means that supply chains are and supply chain coordination is a natural area of interest for me. And these are the type of problems that I have been solving with the blockchain technology. Okay, but one of the other motivations, or the rather the original motivation that spurred the Bitcoin network, right, about which we will learn soon, right, is the following, right? So if we all do e-commerce, right? We buy stuff on either Amazon or even purchasing a ticket on IRCTC, wherever it is, right? We do electronic transactions, right? And one thing you will notice is that banks or some other form of intermediaries are involved as a trusted intermediary, right? I mean, we are trusting each one of them in every transaction, even though they are not party to those transactions, right? I mean, in real life, suppose we were doing these transactions, right? I mean, we were carrying our paper money. We would not, when I am handing over a note to a shopkeeper, I'm not calling upon a bank to come and say that, okay, this is fine, right? But we are doing that in the world of e-commerce, right? Which means that we are trusting these banks or intermediaries to act fairly, which means that whenever there is a dispute, right, they get to resolve the dispute, right? And therefore, the claim that the original Bitcoin paper made, and which is true, is that as a initiator of the transaction, you are not fully in control of ensuring that your transaction status is final. Okay, this transaction can be reversed by the intermediary within a certain window, right? Even though you may not agree with it. Okay, and this is the problem that the creator of Bitcoin wanted to solve by saying that we don't know whether the person is a he or she, who it is. The person has a pseudonym called Satoshi Nakamoto, which is a Japanese name, but we don't know really whether that person is even Japanese or not, or whether even the person lives in Japan or not. So that person wanted to create a currency, okay, and which has these properties of what exactly you do when you exchange notes, right? I'm the owner of the currency, I am giving it to you, and as long as we both sign this transaction, there's a way to use cryptography to sign a transaction. As long as we both sign that, okay, this is a valid transaction we are entering into, that's it. There is no other third party involved, and the money comes from me to you with the guarantee that the same money, right, that I am giving it to you, I am not using it to pay to someone else, so that money is only spent once. So using the same money for two transactions is called double spend, and that's double spending problem needs to be solved. So this is the problem that the creator of Bitcoin actually went, set about, and that's the problem that they solved. Okay, but at the heart of it, it's the same thing. It's a distributed ledger maintained by a set of parties, right? The models are slightly different, but essentially that's the problem that Bitcoin actually solved. Okay, so I want to take a pause here and just get a sense whether all of you are clear about what is the problem that blockchain is really trying to solve.
Yeah, it's really fantastic. You explained it in very layman kind of language, and it's been very nice. As far as I'm concerned, it's very nice.
Okay, great. Thanks. So we'll go ahead, and that was the goal, right? I really wanted to give a very gentle, simple introduction, right? So that people have something to kind of take back, right? So we will now, what we will do is we will now look at each component of the technology, right? Not in detail, but basically saying what that component gives us, okay? And then we will come back to this question of how does this, these two properties, right? Immutability and consensus are achieved in two different settings, right? I will also talk about those settings, okay? So that's, we are now kind of entering into slightly the deeper waters. Go to the next chart, please. Okay, so basically, let me now define what is blockchain, right? Blockchain refers to a class of ledger technologies that maintain distributed and decentralized. Okay, distributed means they are in different places. Decentralized means that there is no centralized authority controlling the way this ledger moves about. Okay, that's why I'm saying without requiring a trusted entity. The ledger evolves through consensus of the participating entities. I have already said this. The ledger is immutable, as I told you, right? No one can unilaterally change the content of the ledger. And smart contracts can be registered and then executed automatically based on the content of the ledger. The shipment is received and the quality check pass is posted should mean the payment goes unconditionally from manufacturer M to the supplier S, right? That's what a smart contract is, okay? And very important thing is that this ledger is a append only data structure, okay? Which is very different from our normal databases, right? I mean, in databases, we define tables, and tables can be updated both with insertions and deletions of records, right? Whereas a blockchain is an append only ledger, meaning you only add content to the ledger, you never take away anything, and therefore it provides provenance of all the events. Okay, provenance means it tells you what all has happened right from beginning until now. Okay, and nobody can change it because, as I said, the ledger has evolved through consensus and the ledger has the immutable property. Okay, there are a lot of applications that take the advantage of this provenance, right? So people are now talking in terms of applications in which you go to a shop and you are buying an item and you point at its QR code and you get the entire lineage of this particular product. Okay, let's say if it is a food item, it will say that, look, I mean, this actually comes from, this mango juice comes from mango that was harvested by a particular farmer in this farm. It was collected by this particular aggregator, and here was the temperature condition in which it was transported. Then it came to this particular processing facility. It passed this, and this quality check, and then you have got this, and it came to this particular shop 2 days back, and now you are buying it. It gives you the entire provenance of the events. So this is what people are now trying to solve with this particular problem. Okay, and we call the network of peers, right? So now everybody who participate is called a peer because they are all peers, right? I mean, they are all equal to each other, and hence they are called peers. So the network of peers who maintain and leverage this ledger is called as the blockchain network. Okay, it has this ledger, and I have drawn this with a link and a key here. This is basically saying that this has this immutable property. Okay, and yeah, let's go to the next chart. Okay, just a small snapshot of the history of this particular thing. The history actually goes back to 1990s. I'm not talking about it. In 1990s, people actually really worried about creating digital money, and there were a few people who created some initial versions of what they called as digital money. Okay, but we are not going there. We are really starting with Bitcoin. Okay. So today, I don't know. I mean, even if you don't know about blockchain, you would have definitely heard about Bitcoin, because in TV these days there are all kinds of ads about these exchanges that allow you to buy Bitcoin, Ethereum, etc. Right? I hope all of you have seen these ads. Right? So it's no longer an unknown entity. So Bitcoin, right? So August 2008, Bitcoin.org was registered, and then in November, this person Satoshi Nakamoto, whether it's a person or a team of people, we don't know, released this particular paper. Okay, and now it has tens of thousands of citations. I mean, this must be one of the most highly cited papers whose original author we really don't know, the identity of the original authors, right? And in the modern times, of course, we know of a lot of historical results for which we don't know the author, but this is one. And it was called Bitcoin, a peer-to-peer electronic cash system. Okay, and I really encourage all of you to download this paper and read it, because it's a very, very simple paper, 8 to 9 pages, no heavy math, no heavy cryptography, right? And not even heavy philosophical discussion in terms of why such a thing is required, because this is actually a very philosophical topic, I mean, in the Bitcoin community. But the paper is a very simple paper which just describes, we would like to have a system which has these properties, and then gives you an architecture to realize that property. So take a look at that. And one fun fact is that one person called Laszlo Enyaq, right, made the first real world transaction using Bitcoin in May 2010. Okay, and that person basically gave 10,000 Bitcoins, okay, for buying 2 pizzas. And for those of you who keep track of the Bitcoin the value, right? I mean, it's one Bitcoin today is worth tens of thousands US dollars. Okay, so the person really ate the costliest pizzas ever in the history of mankind. Okay, so then came Ethereum. And Ethereum, basically, what it did is that Ether is the cryptocurrency there, just like Bitcoin. What it did is, Bitcoin only had a simple, ability for 2 people to exchange money, nothing else. Ethereum actually developed this entire framework for smart contracts. Okay, and Ethereum started becoming quite popular, and then in 2015 basically is also the time when enterprises, right? I mean, like big technology companies started getting interested in this particular technology, and IBM with a few others released Hyperledger, which is the software that I have most experience with, in December 2015, but it does not have a cryptocurrency of its own. Corda, which was again another similar kind of technology, it also has no cryptocurrency of its own. And then Quorum, which is a permissioned version of Ethereum for financial services. It is backed by JP Morgan Chase Bank. Okay, and then there are specialized payment networks called Ripple, Stellar, etc. Okay, you guys can actually take a look at some of these things when you have time. Let's go to the next chart, please. Okay, so I'll not spend too much time here, but these charts are with Professor Anil Kumar, so you can take it from him and take a look at it. But the idea here is that in general, the way the business happens, wealth gets created, and markets are formed, is that it's not really couple of businesses doing transaction with each other. It's really a network, right? Network of connected customers, suppliers, banks, partners, and so on. They cross geography and regulatory boundaries, right? And they all need to transact with each other, but without. But I mean, they should be able to trust that every transaction they do in such a network scenario is robust, but without necessarily placing trust on any single entity. Okay, so that's the heart of the problem. Go to the next one. So as I said, ledger, we already talked about it. This is the most important component of blockchain technology. It basically says who sent, it just tells us this is the transaction from this is the originator of the transaction, this is the consumer of the transaction, this is the amount of money or goods that was exchanged between them, right? So that's the kind of entries that this particular ledger has. Go to the next one. Participants are the business stakeholders. They could be customers, suppliers, government, regulators, etc. And usually they are part of an organization, right? And they have specific identities and roles. And transaction is basically an asset transfer, right? I mean, somebody gave something to somebody. Right? Contract basically says that if a particular conditions is satisfied, then that some action should automatically take place. Go to the next one. Okay, so again, we will not spend much time here because we saw this, right? We have a network of business entities. Each one is maintaining their own record, and all the messages are point to point, right? And hence very difficult to reconcile the global scenario, which is the situation as it is today. And go to the next chart. And next one. Yeah, this is the problem this is the solution that blockchain provides, is that everybody maintains the same ledger, consensus, provenance, immutability, finality. Okay, go to the next one. Yeah, so these are the four important components, right? So ledger we already talked about, smart contract we talked about, consensus we talked about, privacy is another important one. Okay, so this basically says that in the supply chain coordination example that I gave, supplier 1 supplied component A to manufacturer M, right? Is there a need for supplier 2 to know that supplier 1 supplies component A to M? The answer is no, right? I mean, they need not know, right? Only the transaction really is between two sets of three people. One is the manufacturer, supplier S1 and the assembler T. The second one is manufacturer, supplier 2 and assembler T. Assembler T and manufacturer are common in both these triples, but S1 and S2 need not know each other's transactions. And that kind of privacy that is required in enterprise setting is really what gives rise to two different type of blockchain networks, which is one is the public blockchain networks and second is the private blockchain networks. Go to the next one. Yeah, this I'll not repeat this. I've already talked about this. Next one. Yeah, we talked about this as well. Basically, there is a programming language by which you can define smart contracts, you can register smart contracts, right? And and then these transactions and everybody who's participating in the network execute these smart contracts automatically. Okay, go to the next one. This again, as I told you, right? Participants need the transactions to be private, meaning only those people who need the transaction knowledge need to have. And sometimes you may not want the identity to be linked to a transaction also, right? So that is also possible. I did not talk about this, but we will ignore it for the time being. Okay. But the most important thing is that the cryptography is really the central to all these properties that we are going to talk about. Go to the next one. Okay, consensus, right? I mean, people, those of you who have done a course in distributed computing will know this particular term. This is really a process by which the transactions are verified, right? And in Bitcoin, where we really do not know who are all the participants who are maintaining the ledger. Okay, so anybody can download the Bitcoin software, set up their own hardware in their basement, and start participating in the blockchain network, in the Bitcoin network, right? So therefore, just the set of participants itself is not known in Bitcoin. Okay, so this kind of consensus is really expensive, and very heavy duty cryptographic mining is takes place there. Okay, it's called proof of work. But in the kind of setting that I talked about in the beginning, where let's say it's a supply chain coordination kind of network, where there is just 8 or 10 manufacturers, few hundred suppliers, and few hundred assemblers, and so on, and maybe some shipment entities, etc. The set of participants, and that their identities, right? Then the commitment is possible at a lower cost. Okay, and we will talk about both of them. Then there are other alternatives that have come about, but we will not talk about. Okay, proof of stake, multi-signature, etc. Go to the next one. So here is, yeah. Now, any questions till now? We'll go into the third part of this particular talk, and this is probably this really goes to the right, at the heart of Bitcoin. Any questions, doubts? Okay. Okay. So in Bitcoin, right, or they are called permissionless or public networks. What is the setting? As I said, each one of these people that you see here, they are called miners in the Bitcoin world. But basically, these are all the participants who are maintaining the ledger. Okay. And as I said, anybody can download the piece of code, Bitcoin code from bitcoin.org, and set it up and start running, right? And therefore, we really do not know how many people are there, okay, in the network. We don't know their identities, in the sense that everybody has a simple, public key identity, right? So they have a pair of public key, private key, right? But other than that, we really don't know who they are. Okay. We do not even know what is the computational power that the different participants have. Okay, and we cannot control them. For example, people speculate that in China, the government itself is incentivizing to set up huge data center scale operations to participate in the Bitcoin mining process, right? What's their computational power? We don't know. Can we control it? We can't, right? So that's why it's a very, very difficult situation, and that the participants may be malicious, right? I mean, they may be trying to change the content of the ledger to their advantage, right? So I talked about this double spending problem, right? So they may be trying to actually bypass this protocol and try to actually double spend, right? So all of these things need to be guarded against. Okay, so what are the main ideas behind proof of work protocol, right? One is that we don't run an explicit consensus protocol. Instead, we allow any participant to collect and add what we call as blocks of transactions to the ledger. Okay, so individual transactions are not added one by one, but a block of transactions are added. We basically allow any participant to come forward and say that they want to add a block. Okay, but we make sure that anyone who wants to add a block to the transaction has to expend significant amount of computational power. Okay, so this is very important, and that there is some kind of randomness in the outcome of the computational effort also. Right? So both of these things, I left it out, sorry, but I mean, not only do they have to expend significant amount of computational effort, but there is also a kind of an element of unpredictability in the outcome, even if you have spent a lot of computational effort. So that is one. Second is, we have a mechanism by which a participant who wants to add a block can provide that they did so much work, right? And that's called the proof of work. Okay, and then we arrange the blocks in such a way that the entire chain is irrevocably chained. Okay, we will see what that means, but basically, you know, the blocks are chained together, and they're chained together in such a way that it's difficult to unchain them and create a different chain. Okay, so very important chart. Any questions here on the higher level steps that we are trying to establish? Okay, let's go to the next chart. Okay, so what exactly are we doing? Okay, so let's first look at the picture below. Okay, this is how every block is going to look like. Okay, so every block is going to quote the hash of the previous block's content. Okay, so you know it has this hash, right? So this hash is quoted here. Okay, it contains the list and the details of all the transactions in this particular block, contains the timestamp, it contains something called nonce. I will tell you what it means, but just assume that it contains the nonce, and then it contains a value, a hash value, which is the hash of all these three, in fact just these two things, transaction list and nonce. If you concatenate both of these things, whatever you get, the string, right, a hash of that string is added here. Okay, so this is really important. Okay, so why is this important? Because all of you know a property of the hashing function, right? Hashing functions are one-way functions. Okay, what that means is that it's easy to compute a hash, but it's difficult to reverse compute a hash. Okay, what does that mean? That means that in this particular, okay, I'm pointing here, but I think you will not be able to see. Let's look at the second block, right? Let's say that there were 10 transactions there. So if you concatenate this particular thing called nonce, and then those transactions, 10 transactions, you get a particular hash, right? So it's very easy to compute that hash. Okay, that's the property of a one-way function. But suppose you want to change the content of one of the transactions. Okay, you want to take out one transaction, add another dummy transaction. Okay, such that now this new list of 10 transactions concatenated with the nonce gives rise to the same hash. Okay, that is extremely difficult to do. Okay, or more or less impossible to do. Okay, and that's the reason why this, you know, this immutable property that I told. Once you have agreed on a chained block of transactions, it's very difficult to go back and change the content of any of the transactions while keeping the hashes same. Okay, because everybody knows the sequence of hashes. Okay, so that's the most important critical part. Okay, now what is this nonce, right? So this is really the challenge, right? What it says is that at every point in time there is something called a difficulty level which is maintained. Okay, it's just a number. Difficulty level basically says, you know, how many leading zeros are there. Okay, so there is something called a leading level, and what you have to do, anybody who, as I told, right, anybody is free to add a block. Anybody can come and add these blocks. Nobody is prevented from adding a block. Okay, but what they have to do is, they have to, when they are adding a set of transactions, they will, of course, they will know the previous hash. There is no challenge here. They know the list of transactions. They can add any list of transactions. They can even omit some of the transactions that have come to the network, etc. Nobody, they have complete freedom to choose the set of transactions. But this is the most important thing. Okay, they have to find these nonce. Okay, so this is the search problem. They have to find a nonce which has the following property, that when you hash this nonce, right, concatenated with the previous hash, concatenated with the transactions, the content of the transactions that they have included, is below a particular difficulty level, right? So for example, I have said that I want 15 leading zeros when you do the hash, right? What that means is that I have to find a nonce such that when I do this concatenation along with this nonce and take a hash, I get a number which is 15, which has 15 leading zeros. This is a very important point. I don't know if it is not clear to you, just let me know. Okay, I'll explain it again. But this is where the heart of Bitcoin is. Okay, very important. I don't know, I mean, it's not a very obvious thing, so please think about it, right? Anybody can add these blocks of transactions. Nobody is in the network is controlling it. Okay, anybody can do it, but there is only one challenge that they have to meet, which is that for the set of transactions that they are including in the block, right, they have to find this unknown quantity called nonce. Okay, number used only once. Okay, so that's why it's called nonce. Okay, this, they have to search for this nonce such that when you concatenate the content of the transactions, hash of the previous block, and this nonce, and you hash it, right, you should get, let's say if the difficulty level is 15, you should get 15 leading zeros. Okay, and that is why this is difficult, because the hash function, as I told you, is a one-way function. Okay, given the content which needs to be hashed, doing the hash is easy. It's a very simple computational process. But given a hash, right, given a hash, reverse computing the content which can give rise to this hash is very difficult, or it is assumed that it is not possible to do except by exhaustive search, right? I mean, try each potential value of the nonce one by one, which is very, very difficult. Is this understood? Okay. Okay, so this is what happens. And then when a new block is added, okay, many people may be trying to add. Okay, what basically happens is that people will go with that proposer, that peer who proposes the longest chain. Okay, so the longest chain is adopted at every point in time. Okay, so this is the really the essence of the Bitcoin protocol. I'm not going to give you the correctness proof here because it really requires far more time, but wanted to give you the heart of what Bitcoin protocol is. Go to the next chart, please. Now, in the permission networks, the kind of things that I told you in the beginning, the setting is somewhat simpler. Okay, number of participants is known. Identity of the participants is also known, but the participants could be malicious. Okay, meaning that they may be trying to act in a dishonest manner. Okay, if they can try to cheat, if they can cheat without getting caught, they will try to cheat. Okay, so that's what it means. So here the solution is that, the fact is that this problem is exactly same as a very classic distributed computing problem, which is called as state replication with Byzantine fault tolerance. Byzantine means somebody can act very malicious. Fault tolerance means that the faults can be either honest faults or Byzantine faults. And what you are trying to do is basically replicate the state, and here the ledger basically means the state. Okay, and this is a very well-known problem in distributed computing, studied for decades. Okay, but there was a breakthrough solution in the late 1990s by two people in MIT, Castro and Liskov, right? And they called their protocol as Practical Byzantine Fault Tolerance Protocol, PBFT. Okay, and this is what is used in such networks, in networks where the set of participants, so the set of identities are there, but they could be malicious, right? Here the algorithms are simple. There is no that completely humongous cryptographic challenge that people need to solve, like the one in Bitcoin. Here they just participate in a voting protocol at every round, and the voting decides how the ledger is going to move forward. Okay, so these are the two worlds. One is the Bitcoin world that we talked about. Anybody can join, anybody can propose a block of transaction, and we still want to ensure that there's not going to be double spend and that the content is immutable. And I explained to you how that is achieved through this proof of work protocol. And then we have this other world, which is the world where I have worked mostly, is where the number of participants and identity is known, but they could be malicious, and we use traditional distributed computing protocols to solve that problem. Okay. So any questions? Okay, go to the next chart, please. Okay, so what's the comparison, right, between these two? So network scaling, which is how large a network can a protocol support, right? So that's called network scaling. So the network scaling, proof of work scales seamlessly because it really doesn't care, as I told you, right? The entire protocol is oblivious to the number and identity of participants. So it scales massively from a network point of view. Okay, but PBFT scales only moderately, right? It can scale up to few hundred peers, but not thousands of peers. Transaction throughput, which is very important, and different kind of problems require different transaction throughput. Here, proof of work, which is the Bitcoin world, has very low throughput. Okay, so in Bitcoin, the throughput is 7 transactions per second. Okay, which is like really low. Okay, whereas PBFT, which I talked about, can scale up to thousands of transactions per second, couple of thousands of transactions, which means that it is not really at the scale of what Visa, MasterCard, etc. can handle today. Visa, MasterCard, they can handle about 50,000 to 100,000 transactions per second. But PBFT can still handle about 2,000 to 2,500 transactions per second, and that's good enough for a very, very good large class of problems. And then there's a new protocol that has come up, and a lot of people are adopting it now. Ethereum is going to adopt it sometime very soon. It's called proof of stakes. I'll not tell you what it is, but it's a competitor to proof of work. Okay, and it's considered a promising alternative. I mean, it has interesting properties. It has some drawbacks as well, but this is something that people definitely want to experiment with. Okay, so we have kind of covered 3 parts. Okay, I told you the problem that blockchain solves, then I told you about the components that the technology has, then I told you a little bit about the protocols. Okay, now we will get into an example of a real world experience of implementing and operationalizing a blockchain network. Go to the next chart, please. Okay, so yeah, go to the next chart. Okay, so the problem that we are trying to solve is a very simple one. This is the real problem that we solved in my team in India. Okay, and in fact, anywhere in the world, it was one of the first solutions for this particular problem called supply chain financing. And we solved it for an ecosystem consisting of a financier, in this case Mahindra and Mahindra Finance. Okay, this was in the press, and also you can actually look it up. So Mahindra and Mahindra Finance was the financier. They had a bunch of manufacturers, because Mahindra itself has a auto manufacturing company, and they also have a tractor manufacturing company, and they work with some other auto manufacturing companies. So there was a financier, there were a bunch of auto manufacturers, and then there were a bunch of suppliers to them. Okay, in this scenario here, the buyers will be the auto manufacturers, sellers will be their suppliers. Okay, and here is the state diagram. Okay, what happens? Buyer releases a purchase order, seller raises an invoice, ships goods, and requests receipt. Buyer receives the goods, sends the receipt. After that, the seller, okay, and typically, I mean, again, if you guys have no experience with supply chain, I'll have to tell this and you will have to believe it, but this is the way it works. Unlike what happens when we buy, right? We buy something and we pay money immediately. In these things, buyer will buy something, but we'll say that there is a payment period, okay, 90 days or 180 days or 45 days, etc. So the buyer will pay the seller only after that many days, right? So you supply but get paid 90 days later, and nobody wants to wait for 90 days. So what does the seller do? The seller goes and tells a bank or a financier, saying that, look, I have an invoice here. This invoice is accepted by my buyer, but he is going to pay me only 90 days later. So can you please take this invoice and pay me the money? Okay. And what happens is, this financier says, okay, your invoice is for 100 rupees. I will pay you 98 rupees today, right? But when the buyer pays 100 rupees, that will come to me. Okay, so that is what happens. Okay, so he releases the payment to the seller, then the buyer pays the financier, and everybody is happy in the sense that the seller, instead of getting 100 rupees 90 days later, is happy to get 98 rupees today. And the financier, because they have to make their money work, is happy to give 98 rupees today and get 100 rupees 90 days later. Okay, so this is called supply chain financing. I hope the process and the problem that we are trying to solve is clear. I will tell you what we did in this setting. Okay, any question about the setting? Okay, go to the next chart. Okay. So the actual problem that we solved.
Sorry, Vinayak, just one small thing. What is the financier? Why does he is willing to give 98 rupees today to get 100 rupees later? Means I didn't understand that. What's his?
If you go back to the previous chart.
Yeah.
See, the financier, so financier is like a bank, right? So it's like a loan that they are giving to the seller, okay? And as long as they are satisfied that this invoice is a valid invoice, right?
Yeah, okay.
Then they know that the buyer will pay 100 rupees 90 days later, right?
Yes.
So they are financing the seller, saying that, okay, I'll give you 98 rupees today, but I will recover 100 rupees 90 days later.
Okay.
It's just like the interest.
Yeah. Okay. Now I
And
understand.
it's a very nice, hefty rate of interest that they get.
Yeah. Okay. Yeah. Okay.
But this is a very important problem in the sense that, you know, the context for this is that if you look at the size of the supply chain financing market, right, globally, right, in any economy, for example, if you go to Europe or if you go to US, wherever, right, so the size of the supply chain financing market is anywhere between 4 to 8% of the GDP, okay, and we, you know, which tends to be a very big number, and this powers the economy, right? I mean, because people are now getting money for working capital, and then they are able to do more and more business, right? Whereas in India, the size of the supply chain financing market as of 2019-20, when we did this project, was, believe it or not, just 0.1% of the GDP. Okay, and that's the biggest problem lot of our small suppliers are facing in the, you know, when they do business, right? They are not able to get finance for the transactions that they actually are carrying out in the real world. They have to wait 90 days to get the payment and so on and so forth, right? And that's why, but what is the problem? The problem is that there are some fraudsters in the system as well, and hence the banks are very, very careful in terms of whom they give the money to. That's the problem that we were trying to solve by saying, okay, we'll actually tell you what exactly we did. Go to the next chart. Yeah, so you know what we did, I mean, like the real thing is that we made sure that the bank actually gets to see each and every event when it happens. Okay, so the bank is able to see that the buyer released a purchase order. The bank is able to see that the supplier actually sent the goods and also released an invoice. The bank is also able to see that the buyer has acknowledged the receipt of goods with a goods received notice, right? And therefore the bank is now more comfortable to lower the barrier for financing the suppliers. So that's the way we are actually solving this problem. And an ideal solution here would be that, you know, everybody has their own internal systems, right? I mean, buyers has their ERP, supplier has their ERP, right? And shipping or tracking system, they have their own ERP, right? And an ideal architecture would have been to say that you know, everybody you know, from their system just directly sends events to blockchain network, right? And that would have been an ideal solution. But in reality, what happens, I'll tell you. Go to the next chart. Okay, you know, the first problem is really that of the suppliers. Okay, so the supplier base is like really heterogeneous. As I said, some suppliers are big enough that they run an ERP of their own, right? For example, if you are a large supplier of components like Minda corporations or you know, Mothers and Shumi, etc., right? Then you will run your own ERP, and ERP provides own integration hooks, etc. Then there are some suppliers who are not as big as them, but they use some softwares like Tally, etc., etc. And then there are suppliers who cannot even run a Tally system. They actually run, they have use simple Excel based things, right? And then some suppliers are already on a supplier relation management portal that these buyers would have set up. Okay, so it's a very heterogeneous base. Now, if you look at buyers, right? They have, again, one is ERPs themselves place severe restrictions on how data can be taken out of ERPs, and they have very stringent security requirements in terms of how data flows in and flows out of their system. And look at the third party logistics providers, 3PLs, right? I mean, these are the entities that are required to tell you whether the goods have been transported, what conditions they have been transported under, etc. They have shipping managements. Many of them do not have any management system. Okay, and so that's the bigger problem, right? And then if you look at financiers, right? I mean, typically you will have multiple financiers, right? Each one of them have their own loan management system, and they all use slightly different variants of supply chain financing process, etc. So this is the ground situation. Okay, in this situation, what did we do? Go to the next chart. Okay, what we really did is we ended up building a system in which everybody can either send information to the blockchain network through APIs, or they can use a web application which runs both on laptops as well as on mobile phones, right? And they have the option of even uploading Excel sheets, etc. Okay, so and here, the shipping, some of the trucks, they were actually entering, we had given them a screen and they would make a manual entry even, right? So the whole system was not as automated as you would think, right? But with ERPs, again, we didn't have a real-time integration. We had a batch integration. I mean, the information would flow once in a day instead of in real time, right? And most of the other people, they were using batch, like basically this web-based uploads or manual entry of data, right? We built a system for all those things, and then the set of smart contracts required to maintain the ledger and then execute the smart contracts, right? In this case, smart contract essentially was, I'll tell you two smart contracts. One smart contract says that if there is a valid purchase order, if there is a valid invoice, and if there is a valid goods received notice, then release 98%. I mean, I'm just making up 98%, but there is some actual number that and it is configured by the bank. Release 98% of the invoice amount to the supplier. This is one smart contract. The other smart contract is, if there is a valid purchase order, if there is a valid invoice, if there is a valid goods received notice, exactly after the 90 days period, which is the purchase order period, release money directly to the financier. This is the second smart contract, right? So these are the set of smart contracts that we developed, right? So go to the next chart. Okay. Now, again, right? I mean, it's a blockchain project, and one would think that most of the effort is spent in building the blockchain network, which is really the smart contracts and the network. But here is what businesses really care about, right? I mean, people really care about the look and feel of the web application. That's very, very important. They want to use this information for reporting, right? We need to keep cryptography as a black box. Nobody needs to get exposed to cryptography, right? As I said, all these back-end integrations required to happen, like back-end integration with the ERP, back-end integration with the loan management system, etc. Right? I mean, that takes up quite a bit of effort. And the most important thing is, as I told you, banks especially, like if you are trying to build an integration to their loan management system, or even auto manufacturers, if you are building a batch integration for their ERP, they have extremely stringent security requirements that you have to do, right? You have to satisfy. So all these efforts are involved apart from the blockchain itself. I mean, that's the picture I wanted to kind of give you as to what it really involves, right? It really involves the solution provider to work with not one person, but financiers, suppliers, buyers, third-party logistics, understanding their requirements in terms of how they would like to consume the application, and building out all these things, right? Go to the next chart. If I were to just put an effort, percentage of effort, right, you will see, I mean, the key point here is the actual blockchain network design and smart contract development was just about 20% of the effort. And even here, I am really being liberal. I mean, if I were to, it would probably be 10 to 15%, but I'm just very liberally saying 20%. But most of the other effort is really, like working with the ecosystem and giving them the other things with using which they can actually use a solution like this. Okay, and this is what we did. We did this project in record time actually, and Mahindra and Mahindra Finance, they actually have this in production, and then this is how they do at least part of their supply chain financing for the set of auto manufacturers. Okay, I will stop here. I think I gave you an overview of the technology, some of the underpinnings, and how a real project looks like. If you have any questions, anything, I'm happy to answer.
I have no questions, but I thank you for the wonderful presentation. I mean, at least for me, I understood a lot of things about blockchain. Thank you, Vinayak.
Thank you, Pradeep. Yeah, it's a fascinating field. I mean, and I think
can
we are
see.
just getting started. Of course, I mean, the true blockchain enthusiasts feel that, it will actually change the world. We don't know whether that's going to happen or not. But, in one or the other form, this technology is going to change the way businesses function in next 10, 15 years.
I just wanted to ask you about energy issues involved in this whole blockchain.
In the public blockchain, it's a big problem. So that's what I was saying. So if the kind of networks that I set up, right, that I told about, there we use simple, these Byzantine fault tolerance protocols, right? I mean, these are typical traditional distributed computing protocols which are based on voting, right? So they are not energy, heavy on energy at all. They are not. But Bitcoin is highly, energy consuming by its very nature. But also, I want to say that it is actually solving a very, very, very difficult problem, right? I mean, it's solving a very difficult problem, which is to say that, we will maintain a ledger which has such strong properties as immutability, consensus, right? Without even knowing who are the participants and what their identities are and how much computational power each one of them has, right? So it's solving a very, very big problem, and that's why it consumes a lot of power. And one estimate is that today, as of today, the mining process for blockchain for Bitcoin, I should not say blockchain, for Bitcoin, consumes 0.1 to 0.2% of the overall energy consumption of the world today. Okay, So in a scaled world, you can imagine probably, it will end up consuming a few percentage points of energy, and that is a lot, right?
Yeah, true.
So there is a different way to handle this problem, okay, which is people have now started thinking in terms of what are called level 2 protocols, okay, which is you don't have to come to Bitcoin for all the small transactions you do, right? You do that in a higher level layer, okay. Let's say that I'm just giving an example here. Let's say that for all of Mysore, somebody wants to enable peer-to-peer payment, okay. They set up their own higher level protocol where that happens, and that happens, let's say, far more efficiently because everyone in Mysore, etc., and hence you are able to kind of set up a very simple consensus protocol. But then what you do is you pin the state of your Mysore ledger, right, to Bitcoin once in a while, okay. And therefore, you can guarantee that if some funny thing tends to happen in within the Mysore network, the possibilities of that is minimized because a checkpointing is taking place on Bitcoin periodically, right? But most of the Bitcoin load is taken off by actually doing this lot of transactions in level 2. So this kind of hierarchical consensus kind of setting, where as you go up in the hierarchy, you relax the trust assumptions because you are dealing with smaller set of people, more known people, etc., and you can actually have very efficient consensus mechanisms. But then you build robustness into those consensus mechanisms by allowing them to checkpoint their states periodically into Bitcoin, right? And thereby lowering the overall load that comes onto Bitcoin. That's one of the architectures that people, I will not even say they are experimenting, because this is something that is happening already.
Oh, I see.
Yeah, because micropayments, why do you want to, put it on Bitcoin?
Yeah, I understand. In fact, that was my next question. Why would everybody, if everything is in public domain, why should every record be on public domain available to everybody? But now I understand what you're saying. Yeah.
Any other question?
Audience, if you have any questions, please unmute and ask.
Okay. Thank you. It was a pleasure talking to you guys. The charts are there with Professor Anil Kumar. You can take a look. It's not complete in the sense that I have swept a lot of important details under the carpet, because one is time is less, and then second is that I had a fear that I would lose audience. So I've kept it at a high level so that you get the gist of what is happening. Okay.
Thank you, sir.
Thank you. Bye.